Let's start and welcome to the representation learning lecture. As you can see, this lecture is recorded, so I don't know, behave yourselves. Right, there's my thingy. First, some organization stuff. I hope most of you are in the Rocket Chat channel by now. Anybody not? Alright, if you have not written to Professor Coleman to sign up, then do so. And if you have written to him and are not in Rocket Chat yet, then you will receive some Rocket Chat invitation sometime soon. Today, hopefully. Otherwise, most of the materials will be in a SIBO folder, and we will send you the link to that per mail, just to be sure. So, everything you need to know is in the SIBO, but just to repeat, there will be an exercise each week, which we will grade. The first exercise will come out today and will be due next week. The exercises will make 20% of your grade, but we are nice with grading, so if we see that you made an effort, you will get full points. Yes, so the lecture is this semester is by Nicholas, Tim, who's there in the back, and myself, Felix. I think that's it with organization, unless someone has some concrete question. But yes?
Is the grading for the exercise like 1 or 0, or is it really?
Sorry?
Is the grading for the exercises just like per survey?
Good, like per task is it? It's, I think, you said? Task. We'll see. Probably you have some number of tasks per week, like 3 or 4 tasks usually, and for each of the tasks you get, I think, 0 or 1 point. But it's more depending on the effort and not if it's really correct or not.
I want to say one more thing to the exercises. For those of you who didn't have a lecture before with Professor Coleman, the idea behind this correction is that if you solve the exercise entirely, you'll get the point independent of the quality of your solution. That means if you leave out significant parts of the exercises, let's say like 20%, it's very unlikely you'll get the point, or at least the point for this task. So all we want to see is that you try, basically. It doesn't matter if you have some kind of model, if it's like trained and it does the wrong thing, everything. What we want to see is that you like sat down and spend some time on the exercises, and that's the main criteria for getting the point.
Yep. Okay. Also, what else? So the exercises will be, I think, exclusively programming exercises, maybe some questions thrown in there, but almost exclusively programming. So the deep learning course is not like a formal requirement for this course, but it's highly recommended. So you should know some PyTorch, like the basics of training neural networks. We'll go over some introductory stuff later today in the exercise class, if you're interested in that. But if you're already comfortable with PyTorch, you will probably not see anything new today in the exercise class, at least. So just so you know. And with that said, we can actually start with representation learning. And today I will basically talk about what is representation learning, why are we doing it, and then some more classical approaches to representation learning that are honestly not used that much anymore, but I think are still important for the, well, I don't want to say historical context, but just so that you understand the bigger picture. All right. So usually we have some domain. So it works. Curly X here. Could be images, text, whatever, and we want to learn some prediction on top of that. So Y is the space of predictions here. Examples could be images where we want to detect some object and want to classify the object. So we're mapping an image to a class. Is there a cat, a house, a dog, or something? Or for text, it could be sentiment analysis, which is also like a classification task. So you get a sentence and you want to classify what is the general mood of this sentence. Is it positive, whatever they're talking about, or negative, or something like this? Or speech recognition, you want to transcribe some speech to text or something, and then maybe do more with that. And also like amino acid sequences or DNA, and you want to know what's like the 3D structure that these sequences will fold into, which we'll also talk about a bit much later in this lecture. And of course, these domains are not, it's not really clear cut what is a domain and what isn't. Like if I say images, is the domain of images that are like taken outside with a phone camera the same as medical images taken with a CT machine? Not exactly, but there is some overlap, so it's not really clear cut. Alright, and so usually in machine learning, what you did in the deep learning course or machine learning course, you learn like a function like this. From the domain space directly into the space that we want to predict. So, and now instead of doing this directly, we learn a representation function G in some intermittent space Z. That's called also like the representation space or embedding space or latent space or probably more names. And then we train the classifier on top of it. And we basically do this because well, the goal is that we train one or a couple of representation functions, G, for one domain, and then we can train a lot of different tasks just by some simple model on top of that. So, question already? No, okay. But of course you can interrupt me if you have any questions. Yeah, so the goal is, for example, you have one representation functions for images, and then you can train a simple model on top of that to predict animals or to predict numbers or to predict if a person is smiling or whatever. And so this speeds up training because you only have to learn a big representation model once and then only have to train small models. And also it enables us to train with much more data. Because if we want to learn if there's a smiling person on image, we need labeled data. And we don't have that much labeled data. But if we learn like a representation function, we can learn it with no labels or different kinds of labels or a mixture of some labels or no labels, so we get over that. But the gist is we will be able to use much more data. So here are some quotes from a famous paper about representation learning, which you are encouraged to read. There's a lot of stuff in there that's not really relevant for you anymore, but it's important nonetheless. So representation learning means learning representations of the data that makes it easier to extract useful information when building classifiers or predictors. So I think that's the only really clear-cut definition of what you want. But there are also like more abstract definitions and terms that we'll go over. So like here, the AI must learn to identify and distinguish underlying explanatory factors hidden in the observed low-level sensory data. So the sensory data is the stuff that we actually observe. So the pixels of an image, or the sound waves, or the words and text and the explanatory factors are that what basically are the cause of this. Well, we'll get over this. So, well, that's good. Sorry. There are some terms that we'll hear from time to time, like explanatory factor or factor of variations, which are like very similar terms. The idea is basically that there are some underlying factors that explain why the data is the way that it is. So for example, in images, that would be what's the object, the focus of the image? Is it a cat, is it a house, is it a dog, whatever? Or which rotation is the object? Or is there a shadow, or which shadow? How much lighting is there? Or is the image grainy or not grainy? And of course, there is no like clear set of actual explanatory factors. This is just something more we imagine there is, and not every factor is relevant for every task. So if you just want to classify what animal is in the picture, we don't care about the lightning or lighting. Well, we don't care about lightning either, but we don't care about the rotation or whatever is in the image. But there are still the reasons that cause the image to look like what it actually looks like. So, and there's another term, explaining away, that's sometimes thrown around that I wanted to mention. And that is the phenomenon when some different explanatory factors can become dependent given some observation. So here we have the scenario, we have some security system in our house and we are away from our house, but the security system can go off and we get some notification. And there are basically two reasons why it could go off. So there could be a burglary, there are robbers in the house, that's what we want to know, or there could be an earthquake, because it's somehow sensitive to that. And so there's one sensory input, one data point, also one form of data basically, and either the alarm goes off or not. That's what we actually observe. And there are two underlying possible factors that could explain this observed data. Either it's an earthquake or it's a burglar. So, and both events by itself are quite rare, and we assume that they are like independent. I mean, burglars definitely don't cause earthquakes, and we assume that an earthquake won't stop a determined robber from going to your house. Okay, so now the alarm goes off. And, but you also get some other form of data. You hear in the news that there was an earthquake in your city, where your house is. And then this basically explains why the alarm went off. And therefore it's less likely that it was actually a burglar. So you're not worried anymore, you know it was most likely just an earthquake. So the fact that an earthquake went off explains away the other underlying factor. So that's the basic idea of that. That's yeah, some term that gets thrown around sometimes in some papers. I just thought you should at least have heard of it. Alright, so now we have that. I want to go over some aspects of what makes a good representation, or what we optimally want from of a representation. And after that, we'll finally get into what actually, how to learn representations. Okay, the basic one, it should be smooth in quotation marks. If the two input points are very close together, then the representation should also be very close. That's like the most basic prior that machine learning models have. You can argue that it's not really necessary to even include here, and it's not really relevant for every type of data. So for text, it's not really relevant because it's like discrete data. But so that's basically a given because every model does this on their own. Well, not every model, but every model that we will discuss. Okay. Then we wanted to learn representations in a less or differently supervised case. So I already mentioned this before. We want to use all the data that's available. I mean, there are like so many unlabeled images on the internet, or images with captions that might or might not be wrong, and we want to use all this data somehow. So a good representation learning method should be able to deal with unlabeled data, or maybe a mix of data, and we will discuss some methods that can do that. Okay, then we want our representation to have some kind of invariance with respect to the input, which is kind of already related to the first one. So, for example, if the input is some kind of time series, for example, like we measure pulse or like EKG data, heart rate data, then the representations of 2 points close in time should be also similar. Or like more domain specific for images, if we rotate an image slightly or change the color slightly, we generally want to have a similar representation. Okay, then natural clustering. So lots of kinds of data are somehow connected with some categorical variable. So images, you could say for most images, there's some prominent object in the foreground, well, not for most images, but for some data sets at least. And the category would then be what object it is. And a good representation model should somehow separate this, so that you have chalk. So if we have some kind of 2D representation, the camera only sees this blackboard, right? Well, whatever. I don't plan to write too much on blackboard today anyway. But if we have some representation G from like images to R2, I mean, it's probably not a very good representation because you can't really encode a whole image into real numbers. But we would hope then that if we apply this representation to a set of images, then here is some kind of cluster of dogs, and here is some cluster of cats, and here something else. So that representations of points that share the same variable, the same label, are close together, and the rest is somewhere else. It's also like the basic idea because we humans give things names because our brain somehow through evolution and culture and whatever have learned statistical differences in stuff. So that's why we call this a bottle and this a piece of chalk. And we basically want an optimal representation model to be able to do the things. All right, the next one, multiple explanatory factors. So for each task doesn't need every factor. So like I said before, if we just want to classify what's on the image, we don't need to know, is it big, is it small, is it pointing to left or right, whatever it is on the image, we just want to know what is on the image. But another task, for another task, it might be important. So we want to recover many of these underlying factors. And of course, we don't want to recover every factor because there's some factor like back to images like camera noise. Every time you take a picture, there's some noise on the sensor, and we don't care about that. That's not relevant for most tasks. or maybe it is relevant for some task if your task is finding out with which type of camera your picture was taken. So it's not always exactly clear what kind of factors we all actually want to recover and which we don't. But well, this depends on what kind of tasks we're interested to do at the end of this. So there's generally not like one perfect representation that works for every kind of task on this domain, just for like a lot of tasks. Okay. Then continuing with the underlying factors, we want to kind of disentangle them so that each dimension of the latent variable corresponds to some meaningful variation in the data. So if we don't map to like R2 but to like R100, so we have 100 latent dimensions and we are embedding pictures of faces, then we would maybe want like the first dimension to be which direction is it looking? Is it looking left or right? And the next dimension is the person looking up or down? Next direction, is he wearing glasses or not? Next dimension, is he smiling or not, or something like this? So this is nice if you want like an interpretable representation. Usually we don't get this, but like in an optimal world I would say it is a desirable property. Something that we also don't get is some form of hierarchy in the representation. Well, not directly at least. So there are more abstract features, for example, what kind of animal is it, and more low-level features. Does it have fur? Does it have 4 legs or 6 legs? And the low-level features kind of explain the more high-level features. And it would also be nice to have the representation kind of reflect this hierarchy. But none of the methods that we will talk about in this semester really do this. But it would be nice if this was possible. Furthermore, sparsity. So again, the underlying factors. If we want to classify animals again, and one factor is fur color, that's not relevant if the animal in the picture is a lizard, for example. So we have different factors that are not relevant all the time, so we basically only want to turn on or some of the features. So what this basically means that it might be sensible, not always, but it could be sensible that we want that most dimensions in our representation vectors are 0. And finally, and maybe the most important, the factors in the representation should have some simple dependency, because you want to learn a simple model on top of that. So most of the time a linear model. It doesn't matter if our representation reflects all the underlying factors if we cannot learn with a simple model on top. And some kind of example of more engineered representations are like units in physics. So, for example, you may know that force equals to mass times acceleration. But force and mass and accelerations are also only like representations of the actual physical world. We could also define some new variable, which is like force squared plus 3 or something. And then we don't have such a nice connection between the variables anymore, even though it has like the same information. So the physicists engineered basically these representations so that they have simple dependencies, well, sometimes at least, and we want our model to do the same. Okay, now we have all these criteria which are kind of wishy-washy and more like abstract. but how do we actually know if one representation is better than another? And one of the most popular ways is linear probing. So we learn a representation, on images for example, and then we take another data set, maybe a small data set, but a data set that is labeled. And then we just train a small linear head on top of this. So here with the usual cross entropy term, and W is just a matrix. So I hope you all are kind of familiar what I mean when I say linear layer and cross entropy. Okay, great. But that's basically it, and then we just measure the accuracy on the test set. And if we get a better accuracy, then it's a better representation, maybe. Because it always depends on what kind of tasks we are interested in. If we are training on images, should we then do this linear probing on ImageNet, like the big high-resolution labeled dataset, or something small, like Cypher 10? Maybe one model is better there, one model is better there. Who knows? That's, well, task dependent. What's important is you can't really say anything from the training loss, because if you train your model on your representation model, G, you also will have some kind of loss, and some models will have lower loss on the data, and this might help you to to do hyperparameter tuning, but it really doesn't tell you anything if one representation is better than another. So some huge model might have tiny loss on your representation objective, which I will tell you about in a little bit what they could be, but this doesn't mean it's actually better in like this linear probing metric. And it doesn't have to be like linear probing. There are other ways which are popular, like k-nearest neighbors, but in general you train some simple, small classifier on top of the representation. Alright, that was all the definition stuff. Now we can start how we can actually learn representations. Any questions so far? Okay. Okay, now I will go through some different viewpoints or objectives that we can use to learn representations. So the first one, maybe the most important one, we use deep learning, then some maximum likelihood methods, autoencoders, which will be the topic of this week's exercise, and then more stuff. Yes?
Is it usually the case that the representations are like lower dimensional or like embeddings, or is it not?
Yeah, usually I would say it is the case, but not always necessarily. Because like learning on low dimensional data is usually easier, so that's why we would prefer this, and it's also faster, but it's not necessarily always the case. Yes?
Is one of the targets having the representation kinda interpretable, or it's usually not?
So what's a human interpreter?
Yeah, human interpreter.
No. I mean, it would be nice, and there is some work on this, but usually this is not like the main concern, and it usually, unfortunately, also doesn't happen by itself. Okay, so there was also autoencoders will be the topic of this week's exercise. So that will be important. Then a tiny little bit about manifolds. And mutual information maximization, not today, but this will be important later in 3 weeks or so. So the most important thing today will be really about autoencoders. The rest is more context. And like I said, these are like different viewpoints of how to do representation learning. They're not like mutually exclusive, and they are not like, it's not an exhaustive list. You can think of representation learning in different ways. These are just some of them. Okay, so since I hope, like I said, most of you have heard deep learning, you know that in deep learning our models are just a sequence of smaller, simpler models behind each other. So F1, oops, and so on up. What's going on here? Are just layers, and capital L is the number of layers. And what we can do, we can train some deep learning model, some deep neural network on some task, for example, classifying images on ImageNet, and then just cut off the last layer, and tada, we have our representation function. So, because deep learning inherently learns representations. It learns representations that are important for this task. So in this example, important for object classification. But it turns out, if you actually do this, so if you learn a classifier on ImageNet and just chop the last layer off, there are also a lot of other information in this layer before the layer before the last, the penultimate layer, that you can use for a lot of stuff. So that's basically transfer learning, what we're doing there. We are learning on one task, classifying images, and then we apply this to some different task. Maybe also classify images, but maybe different types of classes. But this also, of course, requires that we have labeled data to train our model in the first place. So here, an image, some kind of figure. We have our image. It goes in the convolutional neural network. Often, if we use images, we could use some form of convolutional network. Of course, not always. Like vision transformers are getting very popular, and we will use those too in this lecture. But then there's some linear layer at the end, or maybe multiple linear layers, and we just chop them off and use this layer in the middle as a representation. And it's like really important to know that this doesn't work for every kind of machine learning model, because right now, probably most of you, if you think of machine learning, you think of deep learning and neural networks. But that wasn't like always the time. There was a time when like kernel machines and tree models were like more popular, and then you can't do that. Then these models are not just a simple sequence of layers that you can just chop in half wherever you want. So that's a really important property of neural networks. There's also the idea, basically, if you choose a lower level layer, so one that is closer to the input, then you will get more less abstract features. So right at the beginning, if you take a layer, the features you might get are the edges, or which color is the general images. And if you take a later layer, you might get some more meaningful information in there. Okay, but like I said, you still need some task with labeled data to learn your original function. Or maybe you don't, maybe just make some task up and train on that. So this will be the topic of the next 2 weeks, pretext tasks. How basically can we train neural networks without any task? One example would be like rotation prediction. We rotate some image, and our network should learn in which direction we have rotated it. Because most like natural images have some kind of natural rotation. At least like if we do 90-degree rotation. And if a network learns to correctly predict this rotation, then the hope is that it has has understood the data somehow. But we will go more in detail with this next week with Nicholas. Okay, now some more math. Maximum likelihood estimation methods. So usually assume that we have some data distribution P of x, so that's not written there now, but assume P of x like our data distribution. And we want the distribution over our latent variable, over our representation, to have some fixed distribution. Some fixed simple distribution, for example, just normal distribution. There's something that we can just choose. Because, of course, depending on what kind of representation we learn, we could get different distributions in our latent space, but for now let's just assume, not assume, let's basically require that our latent distribution is given, like the normal distribution, for example. What we then can do, we can parameterize some kind of decoder, some kind of functions that takes the latent variable z, the underlying explanatory factor, and generates basically the data, or the data distribution rather. So the idea is if z is an underlying factor, like what kind of animal is an image, how is it rotated, then our model p theta with parameters theta takes this latent information and turns it into some distribution over images actually. And then, at least mathematically, we can write down this integral. I hope you are familiar with like the basic probability rules. Otherwise, you can do something about this in the exercise later. And then we can just maximize this. And then hopefully there's some information about the data structure learned by our encoder p theta without the need for any labels. There's just two problems. How do we actually maximize this? And how do we actually get representation from this? Because p theta here, this likelihood function, basically maps from z, from latent space, to x, to the input space. And we basically want to have the exact opposite of that. So we want the posterior, p z given x. So there should also be a theta here, because it also depends on the parameter theta. And we can use Bayes' rule and write it down, but we cannot compute this generally. And even if we could compute this, then this is just a probability distribution. In reality, we really want a function that takes an x and maps it to a z. So how do we turn our probability distribution in a function? So there are a couple of ways, but the most intuitive one maybe are we just take the argmax, we take the z that maximizes this learned posterior, or maybe we can even take the expectation over this. Both things that are not easy to calculate. So for some distributions, p x given z, this can be actually computed. If we have here a really small model with a couple of like 2 linear layers, there are actually ways to compute this analytically, the posterior and everything. Even then it's still very complicated. But the problem is this function here must be somehow very expressive. So we have our simple latent distribution where the underlying factors are supposed to be disentangled and nice and simple relationship. And this is supposed to turn into an image which has like really complicated relationships between its dimensions. And this won't be possible with like a small network. So this needs to be some bigger function, some big modeled by some big network. And in this case, we can't compute these anymore. So these are really difficult problems, even though like statistically it might be like the most obvious way to just maximize the likelihood. I mean, if you have come from like a more statistical, less deep learning background, this might be the obvious approach, but just really hard for data we actually care about. What we could do is do some variational approaches. So like a variational autoencoder. I don't want to get too in depth about this, so I think most of you probably heard this in deep learning. The basic idea is you replace your posterior with some different functions, with different parameters, and then you can maximize an approximation, a lower bound of the likelihood. And if you choose these parameterizations Q in a nice way, then you can get some form of representation out of this. You can do this, and there are ways to improve this for representation learning, but it doesn't work that well. So, but that is a way how you can learn an autoencoder. So this might be interesting because usually when you think about autoencoders, you think about a generative model. You will want to use it to generate data. But we can also use it the other way around, to embed data into a low-dimensional space, or a simpler space at least. And then, right, PCA. So, I hope you all know PCA, Principal Component Analysis. Short recap. If you have data like this, PCA finds the directions with the highest variance, and then we can just take these directions and ignore the rest. So I talk about PCA here because there's like interpretations from different viewpoints. So you can interpret this as probabilistic method, you can view it as a manifold learning method, or you can even view it as an autoencoder method. So, but now, for now, we are viewing it as a probabilistic method. So, you don't need to know how PCA works in detail. It's just important to know that it learns some matrix V consisting of some eigenvectors from the data, and then you just multiply the transpose of this matrix to get your embedding Z. So how is this probabilistic? Well, you can do something like this. You say the posterior is just a zero-centered normal distribution, where the variance is the actual variance that we get if you apply PCA to our data, and our likelihood is given like this. And then the V from PCA will actually be an optimal solution for this. So this likelihood is really simple. It's just a linear dependency, so it cannot learn much. But this is just one of the cases where you can actually solve this analytically to get the posterior, and then the expectation of the posterior. And if you're interested in that, you can look up explanatory factor analysis, and there's a whole bunch more about this. But I just introduced it to have like PCA as a kind of running example. And there are a bunch more probabilistic methods that you really don't need to know, like restricted Boltzmann machines and deep belief networks. And they all use some kind of fancy statistics and sampling to compute the postteriors and so on. But my point is just likelihood methods are really hard. Even if they're like statistical nice idea, we just maximize the likelihood, they are hard to do in practice. What you can do, you can mix likelihood methods with deep learning. So you can have some autoregressive models, so for example some kind of RNN, recursive neural network, that learns to like predict the next word in a sentence, that also learns some kind of representation, and then you just can again cut off the last layer and you have some form of representation. So not the best kind of representation, we'll talk more about text representations in 2 weeks, but that's generally something you can do. Or you can learn any kind of generative model. You could learn like a gun and take the discriminator now, take the discriminator and just cut off the last layers, and you have some form of representation. Is it very good? Probably not, but in theory you could do this. Okay, now autoencoders. Again, this is important because the exercise will be about this. So I think you all have the basic idea of what an autoencoder is, right? We have two networks this time, our encoder function G, which will be our representation function, parameterized by our parameters theta, and then some decoder function D with different parameters nu. And we basically want to be able to reconstruct the image, or doesn't have to be an image, can be any data point. So it gets encoded by G and then decoded again by D, and it's supposed to be similar to X. And here again, we have some form of distribution on our latent space, but this time it's dependent on theta, on the parameter of the encoder. If you have a different encoder, then you will have a different distribution on latent space. And in the section before, with the maximum likelihood estimations, our distribution was fixed. So this time we cannot do likelihood maximization. This won't work. I mean, there are exceptions, of course, like a variation autoencoder is a form of autoencoder where we enforce the distribution of latent space to have some specific form. But generally, if the decoder changes, then also the distribution on the latent space changes. Okay, so how do we actually learn it? And how do we stop G from just learning the identity? Because if G is the identity and D is the identity function, then it can always reconstruct the input perfectly, but it hasn't learned anything. Okay, so what's the most simplest way to prevent this? We already had it. Yes?
Dropouts, probably. Dropouts.
Yes, that's one possibility, but just like from the architecture, how should the space Z be? Yes?
Make the dimension of Z less than
Yes, yeah, exactly. So this is like the most obvious, easiest one. If X is like a couple of thousand dimensions, maybe just make Z 100 dimensions. And then it has to squeeze all the information in the 100-dimensional space. So we just minimize this function here, over our data, where L is some kind of reconstruction loss. Could be something simple like mean squared error, or any other norm, or any other reconstruction loss that's appropriate for your kind of data. But for now, for the exercise, it will be mean squared error. And look, PCA is back again. PCA can be seen as a form of an autoencoder. If we say that both the encoder and decoder must be linear, and if we say the function, the loss function, the reconstruction loss is the mean squared error, then PCA, the PCA will actually be an optimal solution for this loss. Or to be more precise, if G is linear, then the weights are some kind of matrix, right? And this matrix then will span the same subspace as the eigenvectors in PCA. So now we have the same representation methods, PCA, but viewed in a different way. Okay, so, but there are some problems with this. There are lots of information in our data that we don't care about, like low-level pixel information. Where exactly is the image? Is it a little bit more left or more right? This function has, this method has problems with learning these invariances because it reconstructs everything. So, okay, before we talk about this, or maybe, okay, a little bit out of order. So a different version of autoencoders are denoising autoencoders. First, we put some noise on our image, or form of data. So the simplest way would be we just add some Gaussian noise on there. A little bit of noise, I don't know any different word apparently. And you try to reconstruct the original image. So you have the image, put noise on there, encode it, decode it, and this then should be your original image. So the encoder-decoder stack must learn to denoise the image basically. So how can we think about this geometrically? If we think that our data lies in like a low dimensional manifold, so if our data line is on this black line here, if you put random noise on there, then it will probably be pushed away from this line. And our encoder-decoder has no way of knowing where the original point is. But a good guess basically is to just move it back onto the manifold. So we basically learn like a vector field that points towards the manifold, that points towards regions of high likelihood. And actually there's some kind of connection to like score matching. So in statistics we have the score function, the gradient of the log likelihood, and in some very specific simple cases you can actually prove that the encoder-decoder stack will learn exactly this function. So learn the direction in which the likelihood goes up. And this is obviously nice. And you can also choose which kind of noise we put in there to kind of control what kind of invariances we want to have. So we can just, in the easiest case, just put like Gaussian noise in there. But if we want to say we want a representation that is invariant to rotation, we can instead put also some rotation on there, or some color noise. So that's a lot of nice things that we can do with denoising autoencoders. But going back, there are also sparse autoencoders. They're not terribly important right now, but I mentioned before that a good representation should be somehow sparse. Lots of zeros in representation, and we can just do this by penalizing the representation with some kind of function omega. It could be the L1 norm or something else. And which is important about both sparse autoencoders and denoising autoencoders, they can learn features even if we have an overcomplete latent space. So before I didn't say it, I think, but if the dimension of the latent space is lower, we call this undercomplete. So and then basically it has to learn to compress the data somehow. But now we could also choose an overcomplete setting, so where the dimension of latent space is actually larger. And if we put enough noise on there, it will still learn something meaningful. Sometimes it does make sense to have like a larger dimension there, because it could be that the input dimensions are not very many, but the dimensions are like very complicated related, and you need to somehow project them in a higher dimension so that they become simple and with a linear relationship. Like a kind of artificial example would be we have like 2D data where with two classes, so you have circles here and crosses around, and is this a good representation of the data? It's not perfect because you cannot learn a linear classifier on top that will separate the circles from the crosses. But we could learn some kind of projection in 3D space. So basically where the x's are like pushed away from the blackboard and the dots and circles are pushed inwards, and then the blackboard would be like a nice linear separator. So sometimes it's like necessary to move to higher dimensions so that we can have linear relationships. Of course, what we can also do is basically map the x's this way from the blackboard and the circles inward to the blackboard, and just keep this dimension. Then we have a nice single dimension representation, but well, there's no perfect answer every time. And there are a lot of more different ways to penalize sparsity, but they're really important right now. So the most simple one is just the L1 norm. We just add the absolute values of the norm vectors, of the representation vectors. Okay. And there's also another nice type of autoencoder, the contractive autoencoder, which actually behaves very similarly to a denoising autoencoder with Gaussian noise. So what we're doing here, we're penalizing the Jacobian matrix of the encoder. So what does it mean to have a small Jacobian matrix? if we think about what happens if G is linear, if G is linear, then Jacobian matrix is just G itself, basically, or like the matrix that represents G. And if this has a small norm, so F here stands for the Frobenius norm, but that's not really that important, that basically means that points that are very close are even closer in the encoding space. So that's what it means to be contractive. It pulls points together. So what will happen if we have, what I'm talking about. So basically, if we have some input in this red region here, it wants to pull them all together to like a single point, and which results in them being on the manifold again. But the difference to the denoising autoencoder is that we can kind of compute this here analytically, or with like Autograd in PyTorch. I mean, it's slow if the network is actually big, so we don't do this. But in theory, it's possible, and it could be faster than the denoising autoencoder. Because if we train our denoising autoencoder, then we actually have to sample noise, right? We take an image, then we sample noise, and then we minimize this. And we might have to sample lots of noisy versions of the same image for this to properly work, and this could take a long time. And the contractive autoencoder learns this without any randomness, and this is a nice thing to have. Also, we have like a parameter here where you can have a trade-off between the representation and how insensitive it is supposed to be to noise. And in the denoising autoencoder, we don't have a trade-off directly. I mean, you can control the noise size. You can control the sigma here. So if you put more noise on this, then the reconstructions will be worse, but it will have more invariance. Alright, that's it about autoencoders. And we're already at our last very small topic, manifold learning. If you have heard deep learning, like I said to the NTN time today, you will have heard about the manifold hypothesis. So the idea that actual real-world data lies in some kind of lower dimensional, much lower dimensional manifold, which is on the one hand the idea that there are like a small number of explanatory factors. So an image might have actually millions of dimensions, so millions of pixels, but the underlying factors are maybe a couple of thousand or something. So that's the one half of the manifold hypothesis. But the other half is that if we vary these factors, we get some nice geometric surface-like thing. And back again, PCA. So PCA learns a linear manifold. If our data actually lies close to a plane, let's say, if our data is three-dimensional, but the points lie close to a plane, then PCA is perfect because PCA learns this plane. So the prior of PCA is that our data lies close to a linear manifold, which of course is usually not the case. So we need something else. But learning about manifolds is nice because we can think about like tangential and orthogonal directions at one point. So if we had one point here, we can basically move with the manifold or completely opposite to it. And if we move orthogonal, so like with this here, with this in this direction, we move away from the manifold and we get data that doesn't appear. But if we move in any tangential direction, the idea is that we'll change the underlying factors of variation. So if we have images of faces and we just linearly move anywhere, then we don't get a nice different face. But the idea is, if we move along the manifold, then the images of the faces will basically move from one face to the next face is slightly different. For example, from a man smiling to the same man not smiling. And then if we move in a different direction on the manifold, we get from a man smiling to a woman smiling or something like this. So how do we actually learn this? More about tangent spaces. You can kind of approximate where the tangent space is and then actually do this. So this was actually done using contractive autoencoders, but it's not really important how. So they took MNIST and for an input point they learned where's the direction of the manifold and then move along this direction and see what we get. And it turns out that we actually get recognizable digits, which is nice to know, which kind of means that there might be something to this manifold hypothesis, at least for MNIST. For higher dimensions, you really can't do this anymore because we don't have enough data to actually learn anything meaningful in this way. But if we move along the tangent, we get the same image, but like varied somehow. Whereas if we just move in a random direction, we just would get a noisy image. And this is usually learned with some kind of non-parametric methods, with some kind of neighborhood graph methods. So you have your data, and for each data point you kind of compute your nearest neighbors, and you have kind of graph, and then you can do stuff on there, like local linear embeddings or isomap. You might have heard of some of these. And you can use them as dimensional reduction methods, but they're difficult to use as representation learning methods because you don't actually learn a function. You learn a mapping from your training set to a lower dimensional space, but it's not easy to like take a new point and put it in there. So I just included the manifold stuff for completeness, but that's really not terribly important, just so you know that's a way to think about it. And there are methods that assume that the data lies on a manifold. So the word manifold will definitely come up again later in lecture, I think. But these specific methods, isomap, local linear embeddings, and so on, are not terribly important. So most important today were like the autoencoders, like the undercomplete autoencoder and the denoising autoencoder, and I'd say this one you should also know a little bit. Okay, that's it with the topics for today. Are there any questions? No, which usually means it was really bad or really good, and I don't know if this was the second one. Like there were a lot of more abstract concepts today and a lot of overview of stuff, and next week we'll definitely focus more in depth on a single topic per week. So yeah. Yes.
The question is not directly connected to the lecture today, but do you have some literature that you would suggest which could be useful to read?
Like books?
Yeah, like books or papers or like.
Good question. We definitely can put something in the rocket chat. I don't know anything like on the top of my head that's like specifically good for this lecture.
Because information are quite often quite scattered around, so it would be nice to have.
Yeah, and there are definitely some stuff, some blogs and some important papers that we can link to you. Yeah, we'll do it. Okay. So we could end the lecture now and wait for 5:30 to start the exercise. But if you want, you can also just do like a short break of 5 minutes or so, and then who wants to stay can listen to the exercise. And otherwise, I think we'll just cut the lecture short today if there are no other questions. No? Okay, then in about 5 minutes, let's start the exercise, and thanks for listening.